all are in for a treat. Next up, we have Zac Wiliamson, co-founder and CEO of Aztec. Let's have a go.
You. Hey. Oh, thanks everyone. Hi everyone. I'm Zac. Won't repeat what you just said, but yeah. So Aztec is a privacy-first smart contract-capable layer 2 for Ethereum, and we've been in the works for several years now. Had to figure out a few technologies along the way, things like Plonk. But what I want to talk about now is effectively talking about how one even enables composable privacy and a smart contract network when everything has to be represented through ZK snarks, and all of these high-level engineering abstractions that developers are used to have to be completely re-replicated from scratch using zero-knowledge solutions. So, do I have a clicker? Do. Yeah. So, I'm going to go through the cryptography, then the architecture. So first of all, what do I mean by private smart contracts? So there's several layers to privacy. You have user anonymity, so you don't know who's sending a transaction. You then have private state variables, so the smart contract that you're calling, all of its state is encrypted. Not only is it encrypted, but it's undetectable whether that state has been modified by a transaction. Then you have this concept of private function execution, where the actual logic of your function is hidden, and this ties in with private contract code, where if you're observing blockchain transactions, you don't even know what contracts are being called by the user, and you don't know who the user is, and you don't know the state that's been changed as a result of that transaction. But you do know that whatever's happened, it's followed the rules. So there was a smart contract that has been deployed, there is code associated with it, and that code has been correctly executed. So yeah, somebody did something to some state of some function of some contract. That's what we mean by privacy. So the real deal, the full Monty. So first, before talking about the cryptography, what I want to talk about is what we want our cryptography to achieve, because that greatly affects the technologies and proving systems that we use, because we have very different requirements to more like traditional transparent ZK technologies. So one main thing is we want this concept of public-private composability. So private state is owned by individual users or groups of users with decryption keys, but a lot of decentralized protocols require the concept of shared state. So for example, the total supply of liquidity within a liquidity pool. So the way we enable this is an asset contract has private functions and public functions. The public functions modify regular account-based state. It can be shared. Private functions modify a more Zcash style UTXO nullifier set arrangement. But instead of these UTXO notes representing like values, they represent arbitrary state that can be interpreted by the smart contracts according to whatever arbitrary means. And the other important thing is that we want contracts to be able to call other contracts, so the composable part, so that you can have the same kind of incentives and network effects as Ethereum, where if I deploy a smart contract, that then becomes a piece of infrastructure that any other protocol or smart contracts can use. And this is rather challenging because, as you probably can tell, these functions are going to be converted into snark circuits. So what do you mean about what does it mean for a function to call another function when these are just snark circuits? How does a circuit call a circuit? That doesn't make any sense. So we have to make it make sense. And the way that we do this is with this relatively newfangled concept of an incrementally verifiable computation scheme. A bit of a mouthful. But this is effectively just an iteration on the concept of recursion, basically being able to verify a proof of knowledge within a snark circuit. So circuits, verifying circuits, verifying circuits. And IVC is a more formal way of describing this, where you basically have an evolving computation. So you have, in our case, each function call is a step in the IVC scheme. What happens is that at each step, one is using some kind of recursion system or something a little bit more advanced, which I'll get into, to sequentially evaluate this user transactions. So we have some unique requirements for our technology because of the nature of what we're doing. Our proofs have to be client-side because, well, they involve secrets. There are workarounds. You could use trusted execution environments, or you could use multi-party computations, but we want our network to not rely on out-of-band network participants as a base model. So we want to be able to prove this stuff client-side, which means very little memory and very little computation. If there is an Aztec DApp that's being represented as a website, that likely means that the proofs are not just being constructed locally on potato hardware, but they're being constructed inside a web browser execution environment, which basically means you're running WASM. And WASM code is about 5 times slower to execute than native code when you're working with number field theory, prime field arithmetic. So this all adds up to saying that basically we have vast limitations on the complexity of the computations that we can perform, yet we must handle complex computations. And we can't just throw hardware at the problem. And so this is the Aztec incremental verifiable computation scheme. I can't zoom in, and I'm guessing nobody here has superhuman vision, so I'll just try to describe at a high level what's going on here. So we have this concept of a kernel circuit, so we very much adopted this nomenclature from the Zexi paper from way back in the day, where what does a kernel circuit do? Well, it takes in a function call, executes the function call, effectively verifies the proof of correctness, and performs consistency checks between any previous kernel circuits that have been called. The idea here is that you have a function call stack represented within the kernel circuit that describes all of the functions to execute. So the idea is in the first step, your function call stack will likely just have one function on it. What the kernel circuit will do is it'll pop that function off the function call stack. That will then, a proof representing that function will then be like verified or accumulated or folded. I'll get into that in a bit. The public inputs of that function call will then be analyzed in the kernel circuit, consistency checks will be performed, and if necessary, additional function calls will be pushed onto the function call stack, because that's what happens when functions call other functions. The idea is that, as a result of that, in the function's public inputs, there's going to be a bunch of inputs reserved for pushing extra, emitting extra function calls. And so this process happens iteratively. So each kernel circuit will recursively aggregate the kernel circuit at the previous step. This is what we mean by IVC. And this entire process continues indefinitely until the function call stack is empty. And then that proof is then given to some third-party rollup prover to include into a rollup block. So there are a few things to notice about this. One of them is, hoo boy, that's a lot of recursive steps for a client-side prover to perform. That's a lot of recursion. So each F that's being fed into K, that's recursion. Each K that's fed into another K, that's recursion. Or in our case, folding. Either way, it's a lot to do. And we're doing this all client-side with limited resources. So that was a key problem that Aztec had to overcome for our architecture to work. And in our view, this kind of architecture is basically the only practical way to provide the kind of smart contract semantics that regular developers are going to expect and be familiar with, that won't require them to understand, like advanced cryptography or handling state trees in strange and unfamiliar ways. So, Goblin. I haven't talked about Goblin plug. So, we use the proto-galaxy folding scheme to accumulate all of these various kernel circuits and function circuits. It's just a more efficient way of doing recursion. That's the way I see it, at least. Formally, it's quite different. But effectively, what it does is it means that we can fold all of these circuits into an accumulator, where, because we're using elliptic curve cryptography, I'll get onto why we're doing that in a bit. The act of validating that folding within a kernel circuit, it's very efficient, apart from the fact that we have to do these things called non-native elliptic curve operations, non-native group operations. Effectively, because we're using elliptic curves, the prime field that we're working over inside a circuit is not the same as the prime field you need to work over to perform elliptic curve arithmetic to verify or fold a proof of a circuit. This is it's an old problem with many solutions of varying quality. And Goblin is our attempt at a coherent solution that is efficient for our needs. Effectively, what Goblin does is it's a form of delegated computation. The idea is that if you need to perform one of these expensive operations in your circuit, you don't. You instead populate a lookup table with the instruction, and in that lookup table is a claim to the result of that instruction. So the idea is you're basically growing a commitment to a table of instructions to be performed over this unpleasant non-native elliptic curve. And then at the very end of the IVC scheme, we have this thing called a translator circuit, which translates this statement about these instructions from your initial elliptic curve to a so-called cycle curve, the type of curve that you would use in a halo-type system, which is that transformation is relatively efficient, and then once you have that, you can then evaluate all of these expensive operations over the elliptic curve that is actually native to those operations, so they become very cheap. Effectively, the abstraction layer that it creates is that it effectively makes all these expensive non-native elliptic curve operations cheap native elliptic curve operations, which means that the folding protocol becomes very, very efficient to evaluate inside a SNARK circuit, which means that we can do all of that expensive, painful IVC client-side. I'll show you some benchmarks in a bit about that. So yeah, it's an accelerating scheme. It's relatively new. We have a HackMD that describes it, and we'll have a proper paper out, hopefully in the next couple of months. So this is kind of our lead applied cryptographer, Cody, put together this goblinized proto-galaxy IVC scheme, where basically these Fs, they're function calls, we have these kernel circuits, and we have this relatively complicated merge and folding scheme system, which means that the individual circuits on the left-hand side of that diagram are relatively low complexity, cheap to evaluate, and these elliptic curve operations, they go into this transcript, this operations queue, that we then process externally via this Goblin-Plonk protocol to make them efficiently evaluated. Right. Well, that's a lot of nonsense and a lot of words. But to try and summarize it, we've had to choose a cryptography tech stack which satisfies some unique requirements. We have very little memory consumption. We have to perform recursion exceptionally quickly with extremely limited resources. We're talking less than like a gigabyte of RAM. And so for that, we really need a folding scheme. Folding schemes are the absolute fastest ways of evaluating recursive compositions. And folding schemes have to work over elliptic curves because they require linearly homomorphic commitments. And then we use Goblin-Plonk to eliminate the remaining expensive part of these folding schemes. And the actual SNARK protocol that we're folding, where all these proofs are happening over, is something we call HONK, which is a variant of ultra hyper Plonk, I believe. So it's Plonk, the original like Plonkish type arithmetization with a log derivative lookup protocol. And then we, instead of doing quotient testing, we used sum checks to remove the need for fast Fourier transforms, which crosses down the memory, and a bunch of custom gates. So this is a linear time proving system with very good constants and very low memory consumption. Particularly when you also add in the fact that recursion in the form of folding is very cheap. It means that it's much more practical to break up large computations into smaller ones so that the overall memory consumption of your device stays low, say a gigabyte. So here's some benchmarks. Now these are very outdated. So these are basically, this is what we did before we went on optimization passes. So they're about at least 5 times slower than what we think we'll get them to once we've actually, focused on making our code fast instead of just making sure it works and is, relatively modular. So what we're measuring here is effectively our estimation of what a moderate complexity Aztec transaction is going to require, which means we have 6 circuits of 128,000 constraints that each represent a function call, and then we have 6 kernel circuits of 128,000 constraints that represent the logic and algorithms that will be required to validate that these function calls have been performed correctly and perform required things like state reads, state updates, consistency checks. So overall, we're talking, 12 times 2 to the 17. So this is a lot of constraints for a phone or for WASM. And this also includes all the incremental verifiable computation schemes, the Goldman-Plonk stuff. And so this all takes about 4 minutes in WASM. So this is not native CPU. This is in WebAssembly. And yeah, we're confident we can get it down to 1 minute for our initial launch of the Aztec network. And I'm actually hopeful we can get it down to 30 seconds. There's lots of scope to optimize this. As I said, we've been focusing more on coherence and visibility of our code above optimizations. But yep, these are the numbers that we have so far. So in the last 5 minutes, I want to talk through the architecture of the Aztec protocol. So I've talked about the cryptography. Okay, so we have this rough IVC scheme concept. We have kernel circuits. We have public and private functions. But this is all, you know, a far cry from a private smart contract network. So how do we take these ingredients and actually cook something with them? There we go. So this is our architecture. So my name has been Zac. Thank you very much. Yeah. So our architecture lead, Mike, this is his baby, his grand design, and I just wanted to show it off because I think it's impressive. But yeah, there's a lot going on here. So this is going to be a very high-level description. First of all, what makes up a user's transaction? So I mentioned before we have this kernel circuit proof that they're going to have. The kernel proof is kind of ready to be consumed by rollup if the call stack, function call stack is empty, because that means, oh, there's no more private things to do. We have a list of the private state variables that need to be added into the encrypted state tree, and the list of nullifiers to add to the nullifier set. We also have a list of public functions to execute, because client-side, we only do the private stuff. We just offload the public stuff to a third party. And also a bunch of the world state that's used to compute the kernel proof. Fair amount of information. And this is the rough transaction flow. So the idea is, on your local device, you start out with this kernel proof. You send it off to a sequencer network to be processed. The sequencers effectively act as block builders. We're going to be using this proposer builder separation, so there'll be the steady state will be much like Ethereum, where you have these block proposers suggesting blocks to builders, but you know. And then those sequencers will farm out the proofs to be constructed to a proven network, and then that hits the rollup contract on Ethereum. So we need to build some private abstractions, and so we have a unique language to handle this all in, because Solidity is an EVM language. The EVM is not privacy compatible. It doesn't have any concept of private state, private functions. And so we wrote our own language, Noir, so that we could provide the contract semantics that we needed to developers whilst ensuring that they could still write their programs efficiently. And we based it on Rust. So it's got very, very similar properties, very similar syntax. They should look very familiar to anyone exploring the Noir language. And so all of the private state is encrypted as these UTXO notes, much like Zcash, except that there's more stuff here. So instead of just a value, you have the address of the contract that produced the note. You have this nonce to ensure non-uniqueness. And then the data that's represented in the note, as well as this storage slot. So like Ethereum, like Solidity, you can have a contract can have multiple storage variables, so they're all assigned slots. And the idea is that the kernel circuit is the one enforcing the contract address in that hash. So your smart contract can't cheat. This ensures that state generated by each contract is unique and does not overlap with one another. And again, we use this concept of nullifiers to ensure private state updates are genuinely unlinkable by observers. The idea is your UTXO tree, when you want to destroy a note, you don't actually mark the note as destroyed. You encrypt the note using a different encryption algorithm and add that to a nullifier set. And the existence of that note in the nullifier set indicates the note has been destroyed. And so you can then prove a note is still alive and hasn't been destroyed by proving the non-existence of its nullifier in the nullifier set. So yeah, this was originally, I believe, pioneered by the zero-coin protocol. And so as I said before, these notes live as storage slots, and these are some of the abstractions that we are providing developers with. So the idea is that they don't have to deal with any of this weird Merkle tree stuff. They just call, they grab the variable they want to mess around with out of storage, they can either remove UTXOs or they can add them. So we haven't completely hidden away the UTXO abstraction because we felt like any attempt to abstract that away would be incomplete and would probably just lead to developers either creating insecure code or not able to produce the kind of code that they would, algorithms they would like to. So private transactions, I'm almost running out of time, so I will try to be fast. Private transactions can kick off public effects, so they can emit public events, they can call public functions. The reason why this can happen is because the private and public functions are kind of executed out of order. And by that I mean a user's private functions are executed first, and then after that the public functions are executed, which means that a private transaction can unilaterally call the public function, but that public function can't have any return parameters, which is an interesting issue, but we have some abstractions to work around that. And similarly, you can call a bunch of events, emit a bunch of events if you desire. And yeah, so the idea here is we have two state trees, the private one, UTXO-based, and an account-based state tree that public functions modify, so that you can provide things like DeFi and like the whole spectrum of applications you expect on Ethereum, but you can selectively encrypt and hide information, for example, things like user identities. And you can also create very powerful account abstraction contracts, because you can do things like sign in with Google, sign in with Apple ID, and that whole process goes hidden from the blockchain. But it means that you can have a contract that is controlled by your Apple ID account, which makes things like account recovery an absolute breeze. And then finally, once you have all of these proofs, we have a kind of a tree-based rollup structure where we want to be able to break down our rollup block into a large number of independent snark circuits, so that we can farm out a lot of independent chunks of work to the prover network, so we can benefit from mass parallelism. And then those proofs are aggregated recursively to form a tree. So assuming you have enough parallel resources, the time required to construct the block proof roughly scales with the log of the block size, which means you can make massive blocks very quickly. And so I believe that is it. Thank you for listening, and thank you for Adam and Cody for some of these slides, which I stole from their earlier presentations. And yeah, go follow us at aztec.network and noirlang.org and play around with what we built. I think you'll be very surprised by where we are.
A heartfelt thank you. That was an exciting update. All right. Thanks again. Big round of applause. Our next panel should be here imminently.